Chapter 17 we'll be talking about temperature and heat. What I'll do is first I'll start by defining what thermal equilibrium is and what thermometers actually measure, how they function. I'll be introducing a new temperature scale. We won't be using the Fahrenheit that we're used to, unfortunately. Talk about how a temperature change is going to affect the length and volume of objects. Then we'll talk about what heat really is and how that's different from temperature. I'll touch on that several times in this lecture. Then we'll talk about heat flow, how that's related to temperature changes and phase changes, as we'll talk about some calorimetry. And then we'll talk about methods of heat flow, conduction, convection, and radiation. So a common misconception is to say objects contain heat. No, they don't actually contain heat. They contain a lot of thermokinetic, or a lot of thermal energy. In our everyday life, we use the terms temperature and heat pretty much interchangeably, even though they have very different physical meanings, and I'll admit I'm utterly guilty of that as well. One thing to note is that in this chapter we'll be looking at macroscopic objects. What that really means is big objects that have some large size associated with that. We'll be taking a look at the microscopic scale, or the very small scale effects on temperature, in the next chapter. So first thing I'll talk about is temperature and thermal equilibrium. It turns out that if you have two objects that are at different temperatures, suppose you have a hot object here and a cold object here, we know that this object is essentially going to have more energy than that object. On a molecular level, the molecules are moving quite a bit faster in the hot tank. And in general, heat tends to flow from hot to cold. So we're going to have this thing called heat flow, which is going to flow from the hot to the cold. If these two objects are now at the same exact temperature, so temperature 1 is going to be equal to temperature 2, then we're going to say that these objects are in thermal equilibrium if and only if they have the same temperature, and so no heat will be flowing between them. So no energy will be transferred from one to the other if they have the same temperature. We use a thermometer to measure temperature, and it actually takes advantage of this thing called thermal equilibrium. If we take our thermometer, you probably had your temperature taken with this as a kid. If you take your thermometer and you stick it into a hot turkey or something like that, it's going to eventually become in thermal equilibrium with the hot turkey. The glass is going to heat up, and then the liquid inside, typically mercury or ethanol, is going to heat up. Because it heats up, it's going to cause an expansion. We'll talk about that in a little bit, and the level of the mercury is going to rise up and up and up, and we can relate the change in length to how much the temperature has risen. So the temperature is in effect also a measure of how much energy an object has, or is at least related to how much energy is in an object. So temperature is not energy, it's kind of like a measure of how much energy an object has. We can extend this idea of thermal equilibrium to talk about three objects, and that introduces what we call the Zeroth Law of thermodynamics. And it was called the Zeroth Law because they came up with the first law, and they came up with the second law, and then the third law, and then they came up with this law, which it turns out is a little bit more fundamental than the other three, and it's actually quite easy to understand. If you have two systems, A and B, and A is in thermal equilibrium with C, so these two objects are have the same temperature, there's going to be no heat flow between them. And we have another system, B and C. These two objects are also in equilibrium, so no heat flow between the two of them. Then we can say that A is also in thermal equilibrium with B. So in a sense, we could say that there's going to be no net heat flow between A and B, simply because both of them are in thermal equilibrium with C. So let's talk a little bit about the temperature scales we'll be using in this classroom, something more like a SI scale. For the Fahrenheit temperature scale, essentially that's what we're used to using in the US. We're one of the few countries that use it, but it is kind of nice because it gives us a large dynamic range for, say, talking about the weather. On this temperature scale, water is going to freeze at 32 and it's going to boil at 212. If you go over to Europe, everything's in Celsius or centigrade, which is a little bit more scientifically based. For the Celsius temperature scale, water is going to freeze at 0 and boil at 100. It is a little bit difficult to tell the temperature because it's not a lot of dynamic range within the scale. Lastly is going to be the Kelvin or absolute temperature scale, which is essentially the same as the Celsius scale, only it's been shifted down such that 0 is going to occur at a temperature at which gas would exert no pressure, or essentially would have no kinetic energy. We cannot actually reach 0 degrees Kelvin, but we can come pretty close. When we're doing calculations, we want to be doing them in the Kelvin scale. We can get away with using the Celsius scale, and I'll talk about that in a little bit. This slide right here shows you how to convert between the various temperature scales. Essentially never work any physics problem in terms of Fahrenheit. Sometimes we can get away with using the Celsius scale. The Kelvin scale, this is the scale that we should always work our physics problems in, and in that case we're just simply taking our Celsius scale and we're adding 273 to it. One thing that you can kind of see is if we're taking a difference, and suppose we're looking at a change in temperature, then in that case the change in temperature for the Celsius scale is going to be equal to the change in temperature for the Kelvin scale. So when we're dealing with problems that deal with a change in temperature, we can get away with using the Celsius scale. If we're looking at a problem where it says it just has the temperature just sitting right there, that temperature needs to be in Kelvin. So if you take a rod and you heat it up, it turns out that it's going to change its length. Suppose we have a rod and it's got an initial temperature and an initial length. If you increase the temperature of the rod, it's going to increase its length just a little bit. And essentially if you double the temperature that you change the rod by, you're going to double how much it changes the length of the rod. The change in length is also going to be related to how long the rod is. If you have a rod of a certain length and you apply some temperature change to it, it's going to change its length by delta L. But if you've got a rod that is now twice as long and you apply the same change in temperature to it, then you're going to get twice the change in length. We can write the change in length there then to be this equation right here, so fairly important equation. I'll work a problem in the work problems using this equation. It says that the change in length is going to be equal to this symbol alpha, which is the coefficient of linear expansion, multiplied by the original length of an object multiplied by how much the temperature has changed from the original temperature. And this alpha right here is going to be material dependent. Some objects are going to expand more than others, the same type of thing. It also applies that if you lower the temperature, it's going to cause an object to contract. Kind of what's going on a molecular level is what we do is we tend to model solid objects as being individual atoms that are bound together by springs, and because this object has some some temperature, some energy associated with it, these springs are actually wobbling up and down. The average distance between the atoms is related to how much kinetic energy the solid object has, which is related to the temperature. Now, if I go ahead and I add some energy to this system, and essentially I'm adding this thing called thermal energy, or have some heat flow into the object, and these atoms are now going to have more kinetic energy, also more potential energy in the spring, so it's going to be vibrating with a larger amplitude. So this average distance between the atoms is going to go up because I've added some heat, some energy, and increased the temperature of the object. That's why an object's going to expand. We can apply this to two dimensions. If we have a cold object and now it's got some length and it's got some width, obviously if you increase the temperature, the length is going to increase in that direction and the width will also increase. It's kind of interesting to think about, if we have a hole in the middle of that guy, the object is going to expand, much like we'd believe. The hole is actually not going to shrink. You might think that it will, but it's actually going to expand. What's happening here is essentially being pulled outward by the fact that the object is getting larger. We can also talk about volume expansion. It works in the same exact way as the linear expansion, where we have a change in volume related to an initial volume and a change in temperature, and this beta is the coefficient of volume expansion, very similar to that coefficient of linear expansion we already talked about. We can take a quick look at tables 17.1 and 17.2. It's going to give us the coefficients of linear expansion for various objects: aluminum, glass, steel. The units for this coefficient of linear expansion is going to be in per degrees Kelvin or per degrees Celsius. It's the same one because we're talking about a change in temperature. In general, every substance is going to behave the volume expansion that I talked about on the last page. Water is actually one exception, and it's actually a very good thing. In general, if you look at the volume of water as a function of temperature, it looks, roughly linear, as you'd expect from the equation on the last slide. But if you look right down here, just close to zero, you're going to see, as the temperature gets lower and lower and lower, the volume gets smaller and smaller and smaller, and then water actually starts to increase its volume. Because of this, the volume is increasing. That means the separation between the molecules is getting larger and larger and larger, so the density of water at 0 degrees is going to be, pretty much every material is going to behave with the volume expansion that I described on the last slide. One exception is going to be water. And if you look at the volume of water over a very large temperature range here, I'm plotting the volume of water and the temperature, you can see that it's roughly linear, kind of like you'd expect from the last slide. Or if you look very close to zero and look at the volume versus temperature, you can see as the temperature goes down and down and down, the volume's getting smaller, as you'd expect. However, below 4 degrees Celsius, the volume is going to start to expand. What that really means is the molecules are going to be further apart, so the density of ice will be less than the density of water, and ice is going to float on top of water. Has huge implications for, say, marine life and everything. The ice is going to form on top, and it's going to insulate a lake and essentially protect the marine life below it. Something else you can kind of see is water is most dense at 4 degrees Celsius, so at the bottom of a very deep lake, the water is going to be 4 degrees Celsius, no warmer, no colder. So have you ever been driving across a bridge and wonder why we have these little grates going across this right here? Or why, when you're driving across the Pennsylvania Turnpike, why your car has to go to junk, to junk, to junk across every single one of those concrete slabs. Well, it turns out that roads are going to have the sun beating down on them, and concrete is going to expand. And if you don't allow the concrete to expand, then we start to get these things called thermal stress and thermal strains related to Young's modulus. So what we do is we put slices in the concrete, or in bridges we have a little region right here where the concrete where we've given the concrete room to expand, so that way we're not stressing out bridges too awful much.